So my interview partner today is Paul Macklin from University of Indiana. Do I have this right?
Indiana University.
Indiana University. So there we go. Yeah, I know Paul for many, many years. We are good friends. We have met each other at many conferences and talked about cancer modeling quite a bit. But Paul, why don't you introduce yourself just quickly?
Well, thanks, Thomas. It's really good to be here, and hello to everyone out there. I'm Paul Macklin. I'm an associate professor of intelligent systems engineering at Indiana University. More recently, I'm the associate dean for undergraduate education, and a lot of my work is agent-based modeling in cancer in particular, and building open source tools like PhysicCell to help a community develop these kinds of models.
Yeah, this PhysicCell has become really big, right? I still remember when you did your first talks on these individual-based models, and they made impressive pictures, but you were not quite sure which way it goes. And so, what made you, or what motivated you to develop it as far as you did?
You know, I think like a lot of things in life, it's a bit of luck and a bit of opportunity, and you just never know what's going to take off. I started developing those. It's funny, I mean, through my PhD, I was really more of a continuum guy. I was doing sharp moving boundary problems with my advisor, John Lowengrab, and had a lot of fun doing that. We built some great models. And then I took my first job after my PhD, looked under a double microscope with a breast pathologist, and said, that doesn't match up. And in particular, saw all those immune cells doing interesting things. We were looking at breast cancer, ductal carcinoma in situ at that point. And so we had cancer cells stuck in a breast duct, which is what we were modeling. But then you look at outside the duct to see all these individual cells clustering and swarming and doing things, all the things that weren't captured in our sharp interface models. And like, it's time to do something a little different. And that got me into agent-based modeling. It took several years. First, we developed just a very specific model of DCIS only. And then we started generalizing, saying, I might do cancer a little bit, and started kind of generalizing it more and more so that it was easier for us to use. And I got to a point where we were writing our first paper then to really make use of it. And we open sourced the code, put it onto GitHub, put out a brief user manual and a preprint, and said, I'm sure no one will ever look at this thing. And much to my amazement, after a few months, we heard from our first great collaborators at Institute Curie, who had found the GitHub repository, had found the preprint, and said, this is exactly what we've been looking for. And we want to give some pieces with Boolean network modeling. This is Gail Latour in particular looking at it back then, and then a whole team afterwards. And then they went away and said, well, that's too bad, that died. And then they came back and said, hey, we're done. and it was just amazing, right? And really I saw the power of people working together on open source for mathematics, software, and research. And seeing that someone found it useful is really what got me to decide to take that plunge and develop it further over the years. And so trying to get it from something that was just barely working, something that just barely worked for DCS, to something generally enough to do many cancer problems, and then to get it from something that we could just barely use ourselves to something that many people would be able to use and hopefully not hate us when they're done. So that drives a lot of work.
No, it generated lots of interest for sure. And you have not just used it for science, you also use it as a teaching tool, right?
That's right. And I tend to find that education and science are linked hand in hand, particularly in open source work, because if you put something out there with no education, no training, no thought to how easy it is to learn, no one will learn to use it, and no one will use it, and your work has no impact. And so we have found over the years that we'll take our tools and we use them and teach in the classroom, undergraduates and graduate students. And we'll find that, they got stuck on this point. They got stuck on this point. So maybe that's an area where we can improve things a little bit. And so we'll go back and refine it and improve the user interface or improve the way we present it, create new training materials, go back. And the next time we teach it goes a little better. And the funny thing is, every time we've improved usability for our students, we've made ourselves more productive researchers because we make it easier for us to build tools. We thought it used to, it's like, it's okay if it takes a week to do this and a week to that. But then we realized, we could just do that really fast and spend our time on the interesting bits. So I found that applying our tools to education has made us better researchers. And having research-grade tools in the classroom, I think, makes for better education.
Yeah. So let's come back to the research then.
Okay.
You started with the promise or with the idea that you can model immune cells and microenvironment of a tumor. do you think this promise is fulfilled to some extent?
Oh, I mean, no work is ever done.
Good.
There are always places for improvement. I think we've reached the point where we can start to do some really interesting things. Like we have a lot of the core fundamental behaviors now, I think, reasonably shored up. Cells can move around, they can secrete chemical factors, can move by chemotaxis, cells can phagocytose other cells can change type, cells can attack each other and cause damage. We have, basically most of the key elements we need for immune modeling. And now we can really start saying, what do these cells really do? Mm-hmm. How do macrophages leverage these different core behaviors and when? Yeah. When do CD8 T cells do things? When do CD4 T cells do things? And how do they interact and decide to use these core behaviors? I think that's our next really big step. And it will definitely expose things that we're missing that we'll have to add into the frameworks. And that's, I think, where it gets really exciting. So
it can always grow, right?
There's always new things. Yeah. I think we're at the point where we can finally discover more systematically what we're missing and to start accumulating bodies of knowledge instead of writing ad hoc. Here's my model today, and then I throw it away and write a new model next week, and then I throw that away. And there's like no reuse. And so it's hard to really learn and accumulate knowledge that way.
Yeah, very nice. Now, what we both experienced in the last, 10, 15 years is a huge explosion of data collection in biology and in medicine, right?
Right.
It's data on tissues, data on cells, single cell genomics, etc. So for you, is this an opportunity or are you scared?
Well, it's both, right? It's a little scary. We need to make sure that what we do is relevant, right? There's always the next person looking for the golden bullet that solves everything and nothing else gets funded and they suck up all the oxygen. And then you realize that didn't work. So you look for the next, magic miracle. And I think the opportunity really is to learn how mathematical modeling really integrates with all these data. I think the place where math can really play a great role in that is you have a lot of data, a lot of genes, a lot of proteins, a lot of RNA, but the core thing that, say, just purely data analysis and bioinformatics has not really met its full promise. It says, yay, we identify gene sets and identify subsets and things like this, but they still don't necessarily connect that molecular scale large data to what cells really do. Mm-hmm. And at the end of the day, it's what cells do that drives a disease or a process. It's the dynamics that makes a disease, not the statics, not that what genes are on or off. I could name a gene anything I want. It can be, the Muppet gene, but it doesn't mean anything unless it's connected to some behavior that the cell does, and it has to be a meaningful behavior. And so I think mathematics has this great opportunity to take that data and learn what behaviors do these genes mean and these proteins mean, and what are the time scales of turning behaviors on or off and deciding what things do and how long they do them. And that's how you go from statics to dynamics in real disease, I think.
Yeah, that's really interesting. And that's probably really hard as well.
Yeah. I think it's a rich problem that will keep us busy for a long time.
Yeah, probably. Yeah. Now, as a last question about young scientists who like to enter this area, how would they go about this? Do you have like a recommendation?
Well, first, just enjoy learning new things. Feel comfortable being uncomfortable, I think. Don't be afraid to jump in and kind of learn by absorption. I think mathematicians, way back when we started, were kind of hide in their office and do things, and maybe every now and then talk to a domain expert, and then run off and we do our math, and then, that was very nice. And it was great. We got great results that way. But there comes a point where you can't go much farther doing that. And I think you need to understand the domain to identify what are the neat questions out there that are floating around. And you can't really get that hiding, you have to immerse and say, I'm going to take a deep dive and just have fun reading about some weird process like neutrophils that spit out DNA and form nets to catch bacteria. Like, well, holy crap, you can't invent stuff like that, right?
No,
you have to go out in the world and find it. Be ready to find the next surprise in biology that might drive your next step in your work, and to learn from other people who are going to help you fill in the pieces on your knowledge. And eventually you're going to learn that shared vocabulary. It's very much like learning a foreign language. You get dropped. For me, it was a very informative experience. I was a college freshman, In the second semester, we took the study abroad program. We flew to Berlin. We arrived like the middle of the night, and just and the next day, there you are in a German family. They don't speak English because smartly they chose East Berliners to host the Americans, so they only spoke German and Russian, and you were like forced to learn. And at first it's noun, verb, noun, and then you start recognizing some of the nouns, you start recognizing some of the verbs, and eventually the language starts to click. And biology is like that too. You immerse in a new environment, and over time you'll start recognizing things and learn the language enough to communicate. And so I think just being open to plunge in somewhere new and don't be afraid of not knowing what's going on and being completely lost for a while, but it'll come around. Yeah. And just talk to lots of people.
Very nice. Yeah. Very good. Yeah. And you are certainly a great role model for people to look up.
I don't know about that.
So, thank you, Paul, for your time here.
Oh, thanks for having me.
This was a wonderful interview, and I'm sure people will love it.
Well, I hope so. Thanks for the opportunity, and thanks for the editing.